Hello, students. We are starting chapter 4, and this chapter, out of all the chapters, is probably the most relevant to day-to-day activity and just examples of chemistry in the real world. We start talking about making solutions. We move into acids and bases. I'll tell you a little bit about ocean acidification, and then we talk about redox reactions, which are the main component, the main type of reaction occurring in batteries. So a lot of what you're going to see in this chapter is going to be really relevant to a lot of the chemical processes. So just starting with molarity and diluting solutions, you may already have seen this in your lab, which is useful. If not, let's just get started with a primer here. When you have a solution, you have a solute. This is something in smaller amount and it's what's dissolved. For example, in salt water, it's salt, sodium chloride. Then you also have something called the solvent. It's present in larger amount and it does the dissolving. For example, the water in salt water. Here's another example, chromium 3 chloride. That's your solute. It's the solid shown here being added to this volumetric flask with a little bit of water in it. It'll dissolve in the water. So this is showing how you make a solution. You have a little bit water first, add your solid, you stir it around a little bit, get it kind of dissolved, and then you add water, enough water so the bottom of the meniscus is to the line in the neck. And the solution is based on the volumetric flask used. There are a lot of different ways to quantify how much stuff is in a solution. We call that concentration. The main unit used is molarity. Molarity is very specific. It's the moles of the solute per liters of the solution. Be very careful. This is not liters of the solvent. It's not liters of water. It's the liters of the final solution when everything's made. That's important because the solute will take up some space as well. So what's really useful is if you're given moles and liters, you can make up a certain molarity solution. Or if you have a certain solution already made up and you know the molarity, you can take out a specified volume and you can actually use this equation, cross multiplying, you can solve for moles. Moles will always be molarity times volume, but the volume does need to be in liters. So we could do a couple classic problems. How many moles of ammonium chloride are in 275 milliliters of a 1.75 molar aqueous ammonium chloride solution? So what you'll do here is you'll start with the volume and you can either plug it into the equation. I notice that some students sometimes have trouble with the algebra or they'll mix certain things, don't know whether to divide or multiply. The other thing you could do is what I'll show is use molarity as a conversion factor. This is the safest way to do it because you'll see the units cancel out. Because sometimes you don't know, do I divide or multiply? I don't know. So in this example, I start with the volume. Again, when you're dealing with molarity, you're going to need to cancel out liters. So you need to convert the milliliters to liters, which effectively, if you do that conversion, you're dividing by 1,000. That's the same as taking the decimal place and moving it 1, 2, 3 to the left. So I get 0.275 liters. Now I use molarity. And again, you need to know, do you multiply or divide? Here, let the units tell you. The big M means moles per liter. So kind of expand the big M and write moles per liter and put the 1.75 moles on top and the 1 liter on the bottom. So the liters cancel and you get 0.481 moles of the ammonium chloride. Here's another one. What's the volume of a 2.5 molar magnesium chloride solution that contains 0.66 moles of magnesium chloride? So here you have a certain number of moles in the molarity. So the reason why this type of problem is important is sometimes you need to run a reaction and you need to know the exact number of moles to add. So here we're using basically You can eventually use this as stoichiometry if you need to run a reaction and combine it with something else. So say I needed 0.66 moles and I know I have this 2.5 molar solution. I would start with the 0.66 moles and then again use molarity as a conversion factor, expand the units to moles per liter. But notice the 2.5 moles, the number will always go with the moles. And here I put it in the denominator so moles cancel, and then it's always per 1 liter. Multiply this out, moles cancel, so 0.66 divided by 2.5 is 0.26 liters. So if I was running a reaction that required 0.66 moles of magnesium chloride, I would use 0.26 liters of this solution. Another really important thing that you might need to do, say you're gonna work in the stock room over the summer, basically a lot of times you'll need to dilute solutions. So you go from a more concentrated solution to a less concentrated. Here, we're just doubling the volume, adding water. What if it's not just doubling the volume? So one thing that's useful is this equation, and I recommend only using this equation in this section. Moles of the concentrated stock solution times the volume of the concentrated stock solution equals m times v of the dilute solution. So the reason why this works is moles times volume in liters is, molarity times volume in liters is moles. So the moles of the concentrated that you use from the stock solution will equal the moles of the diluted solution. Let me back up. We want to make a solution in this volumetric flask. I have some stock solution of a known concentrated concentration in molarity. So I'm going to take a pipette and I'm going to add a certain volume. Then I'm going to dilute that with water. In this case, I'm diluting it so the total volume is 500 milliliters. So the way that you use this equation is a lot of times you're given the molarity of the concentrated dilute and the volume of the dilute, what you want to make. So what you're making is the dilute one, the guys on the right, and you're solving for the volume of the concentrated that you're going to add in the pipette. Okay, let's try this in practice. You guys are going to prepare a 1.0 liter solution of 4.0 molar aqueous barium hydroxide. And what you have available on the shelf is an 8.0 molar solution of barium hydroxide. So you need to dilute it. You may be able to see that you need to go from 8 to 4 so you can dilute it by half. Maybe 500 mils of one, 500 mils of the other. That would work, but a lot of times the numbers aren't as simple. So we'll use the equation. You're going to use M concentrated times V concentrated equals M dilute times V dilute. And again, the volumes I do put in liters. I didn't expand the molarity, but it's moles per liter, moles per liter. And so I just plug it in. The concentrated is 8. And this whole thing on top, what you're preparing are the dilute numbers here on the right side. I multiply these out. That gives me 4. Divide each side by 8. I get 0.50 liters. So notice if you're there and you stop there. The real question is, how do you prepare it or to prepare it? You don't just plug into the equation and stop and just give a number. You have to think about how to prepare it. So have a think what you're actually going to do. Pause and think about that, how the process is going to go. So what you're going to do is use this number that you calculated, the 0.5 liters, and that's what you add. That's of the concentrated 8.0 molar solution, and you're going to put it in the volumetric flask. Then you're going to add enough water to make a 1.0 liter solution. Okay, that ends this section. We'll continue more with other aqueous solutions.